All right, section 2.3, we're going to take a look today at transformations and symmetry. So to start with, we're going to look at a couple of types of transformations. These are called translations. What a translation does is it takes the object exactly like it is and it just moves it somewhere else. So it might move it up and down, that's called a vertical translation, or it might move it left and right. That's called a horizontal translation. And it could do both, and then it has both types of translations as a part of it. But it doesn't change the shape. Okay, so it's what happens when you get in the elevator. It's what happens when you walk across campus. Your body's shape did not change, you just changed where you were located. That's a translation. So a vertical translation happens for an equation when we add or subtract a value on the outside of the equation. So we're going to call our function g of x. And the vertical translation happens when there is a value added or subtracted after our function. If that value is added, right, if it's a positive value, then it shifts up. And if the value is negative, or it looks like it's subtracted, it will shift down. And for example, if you think about your basic x squared graph that you know, if I put a minus 3 on the end of it, it would take that same parabola shape we did last time, it would move down 3. So a vertical translation happens after the equation you already have. A horizontal translation happens inside grouped with x. So on this notation, it looks like this. Now you might say, oh look, x plus h, I saw that happen back on difference quotients. You did. We're not working with h arbitrarily here, though. It will have a value. So it will say like x plus 2 or something like that. But in particular, we have two possibilities. Again, h is positive or h is negative. And it's very interesting because vertical translations do exactly what you expected. Positive, you move up. Negative, you move down. Horizontal translations work backwards. So, write yourself a note that this is sort of backwards of what you might expect. What you might expect is that if you put a positive inside, you'd move to the right, because the right is the positive values on the graph, correct? It moves to the left. So this one is actually a shift left. And if you put a negative inside, you might expect it to move to the left, but when it's grouped inside with x, it actually shifts it to the right. This isn't the only time we're going to see this, but anytime something happens on the outside of the function, in this case like x squared, it's going to happen as you would expect. Moves it up, down, left, right, whatever. I didn't say that right. Up or down, and we're going to do some stretching in a little bit. And then anytime something's grouped inside with the variable x itself before it's being operated on, so it would look something like this. Okay? So it's grouped inside of the squared, right? The squared happens to the grouping of x minus 2. This would actually move it to the right 3. So this moves right 3, while this one moves down 3. So those are called horizontal and vertical translations. They don't change the shape of the graph. So we're going to do a couple of examples of those, and then we're going to talk about another type of transformation. So these are our two examples. As you're doing this, it might be helpful to first just look at it and identify what am I expecting to have happen. So the original graph is the graph of absolute value of x, which is shaped like a V. So we're looking at a V-shaped graph. You know those basic graphs. That's why we did that last time. So this addition of the 2 at the end, how is that going to shift my graph? Close? Up. This one's on the outside of the absolute value, so it's going to shift it up 2. So I'm going to draw in our typical graph that we normally have. Okay? Our typical graph that we normally had would look like that. Right? That's our original graph. So we're going to take that graph and we're going to shift it up 2. So here's my up 1, up 2, and I can actually take this graph and I can physically just move it up 2. That's where I want my graph to be. If it helps you to have both graphs drawn, just make sure you're showing me which one's which. Hang on, I was going to make that one solid. You can do that too. This graph right here is the graph that I'm identifying right now as, what do we call it, g of x, and I'll just label that solid one is g of x. So if you want to draw both of them on there to give yourself sort of a starting spot and then the shifting spot, you can do that. What's going on number 2? What does this do? It moves it to the right 2. All right, so if you want to do it, again, like I just did this one where I drew the basic graph in and then I overlaid it or I shifted it from there, you can do that. You can also move just individual points. For example, the corner where it's, starts the V shape is normally at the origin, and every point has to move left 2. So I can actually move that point left 2 and I can start right here. And then again, the basic V shape means I go up 1 and I go left to the right 1. Right? I mean, that's what happens as I make my V. I go up and left 1, up and right 1. So I can do that from here. So I don't have this point. I have this point right here. And I have, was I going the wrong direction? I was. I'm sorry. We'll just do that. So sorry, not paying attention. Okay, so I moved it to 2. I didn't move it all the way, did I? Here we go. Okay, this isn't working. There we go. Okay. So I moved it to the right 2. Thank you for pointing out that I was not paying attention. And then from that point, I go up 1 and left. I go up 1 and right. And I've got my other 2 points. So this is the graph that I get from shifting this to the right 2. Okay? So those are a couple different ways you can think about graphing these. Just make it very clear that if you do decide to do something like I did in the first one, that you label which one's your final answer. Okay? Okay, so that's one type of transformation, is a shift. Moves it up, down, left, and right. And you can do both. Like I could have a translation that moves it both up and right. You can do that. It just means that I'm going to have 2 things operating on it. So, for example, it might look like, I'll use the same absolute value here that I had before, like this. So if I had these both happening, this piece is telling I'm making a translation that moves right 2. And this translation is moving up 3. So not only am I moving right 2, I'm moving up 3. I'm doing both of them at the same time. So again, you can do it in stages if you want, kind of like I did the first one, or you can simply move that origin spot, right 2, up 3, and start from there, and then create your V shape from there.
Okay, I think you answered this. How do you know the difference between going up and going right?
So if you're going right or left, it has to be inside of the absolute value, or inside of the square, or inside of the square root, or the cube, or whatever you've got going on. So it will have the operation, whatever's happening to it as well. And then if it's on the outside, it's independent of the squaring, or the cubing, or the square rooting, or absolute values. Yeah. All right, the next type of transformation we're going to look at is called a reflection. So a reflection takes a graph, and it either, let's take a look at, or think about an absolute value graph, right? It opens up like this, right? And if you're reflecting it and you're reflecting it down, it reflects it down on over the x-axis, right? That's one kind of reflection. And while it doesn't really change, you can actually reflect it around the y-axis as well, right? It goes like this and it looks exactly the same. So we have those 2 types of reflections. One that reflects it over the x-axis, so it reflects it from top down or bottom up. And then we have one that reflects the left-hand and the right-hand side. So these are mirror images, just like the word reflection means when we talk about our reflection in a mirror. So there's 2 types of reflections. One reflection has the negative occurring inside with x. And the other reflection has the negative occurring on the outside of the function, much like the inside and the outside before. The only difference here is that the outside actually looks like it's occurring in front of it instead of behind it. Okay? But it's still on the outside of the grouping with x. So if you have it grouped inside, this is a reflection over the y-axis. We call it a horizontal reflection. And a real quick, easy one to sort of remind yourself which one's which is, again, if you think about absolute value. So if you took y equals the absolute value of x, and then you considered y equals the absolute value of negative x, Putting an additional negative inside of that graph doesn't change the equation, right? Because you're still going to take the absolute value of it, you're still going to get all the same values. So these two are exactly the same. And the only way that that can be the case is if I'm talking about a reflection that flips it sort of around this axis, right? Like I spun around in front of you. Okay, that's the only way that's going to happen. That's a horizontal reflection. It's reflecting it horizontally, okay? Now the other one, the vertical reflection, so this would be a reflection over the x-axis. It's called a vertical reflection. And if you were imagining this same sort of series of ones, it would look like a negative in front of the absolute value. Okay, so a negative in front of the absolute value changes things. Previously, we had everything positive. Because we had an absolute value, everything comes out positive, and now I have to multiply it by a negative in front of there, right? So it flipped everything down. So on this one, if I were trying to do this, I would end up with a graph that looks like a V upside down instead. Okay, so that's reflections. Sometimes reflections change things. They did on the second example I did there for this particular graph. They didn't on the first one, right? Because it was symmetric already. That's actually what the connection is we're going to talk about in a minute. The next one that we're going to look at is a stretch or a shrink. So if you imagine how our graph is originally shaped, like this, and if you stretch it, it actually looks like it becomes narrower. I'll explain why that makes sense in terms of a stretch. And if you shrink it, it looks flatter. Okay, that's what we're talking about. We're talking about it vertically. So imagine, I keep using absolute value graph because we've been using it, but if you took the edges of the absolute value graph, like you grabbed them, and you stretched them up, it would become skinnier, right? And if you took the absolute value graph and you sort of smushed it down like Play-Doh or like clay, and it squished down, that would be a shrink. It becomes flatter. So those two types actually end up occurring, we're looking at only at verticals here, occurring outside of any of the groupings of X. So they look like this. We either have, sorry, trying to find where I am, k g of x, k times g of x. The k value is either greater than 1, okay? So it's like 5. That's going to be one of them. Or the k value is between 0 and 1. So we're looking at things that are fractional. Okay? Notice I'm not talking about negatives, and the reason I'm not talking about negatives is because we already did that in the reflections section, right? I don't care about the negatives. Negatives flip things. They don't change things stretching or shrinking. So if it's bigger than 1, it's a stretch. It often makes things look skinnier. If it helps you to sort of give it another, descriptive phrase there, it's skinnier. And then the other one is a shrink. And often people think of things looking flatter. So if you were to look at this and go with, I'll give you a couple of examples. F of x equals, I'm going to still use our absolute value because I can. A 2 in front. What happens is that instead of going up 1 and right 1 and right and left 1 like I normally do, I would actually go up 2 and right 1. I end up with something that looks steeper. Right, the slope is almost like slope on this particular description. I would end up with a very narrow or a narrower, anyway, absolute value graph. So this is a stretch. And if the number in front had been a fractional value, so I'll just use 1/2. Instead of going up 1, right and left 1, I would actually go up 1/2, right and left 1. Right, so it ends up sort of broadening out the picture instead of making it as tight as it was before. So this is a shrink. Okay, so those are all of our types of transformations. So what we're going to do now is we're going to be given some examples. We have a couple examples specifically about these types. And then we're going to be looking in a little bit at how to think about it when there's more than one type of transformation going on. So these are the first couple. I already did the first one. Apparently, I was already thinking ahead. Who knew? I'm so sorry. If we can, you want to change it? Let's change it. Let's just change it because we already did this one. How about that? Let's make this negative x squared. Okay, y'all know what this graph of x squared looks like, right? It's a parabola. It's the shape of a U, right, opening upward. So the original graph, and I'll do the same thing I did last time where I draw it dotted and then I'll draw the next one. It looked something like this. I can't do things as well when they're not lines, but it looks something like that. That was my original one. And then if I do this reflection, how will the negative outside reflect it? Will it reflect it like this, right, a horizontal reflection, or will it reflect it over the y-axis, or the x-axis down? Yeah, it'll reflect it down. Noah's telling me it's down. Yeah, it's because it's occurring outside, right, with the negative on the outside. So we, in fact, are going to flip the graph down, and this would be the graph that I've actually got for g of x. So how about this 1/3? What's that going to do to my graph? It's going to shrink it. It's going to make it flatter, like squish it down. So I verbally described how we would do this. We start with the same location because it didn't shift it left, right, or up, or down from the original location. It starts where it was before. But what happens is that instead of going out one and up one, which would be normally here, and I'll draw it in just a sec so you can see it again just like I did a moment ago. Here's my basic graph. I actually go only up 1/3. So I only go up like to right here instead. This is far from precise. I realize that. I apologize. But hopefully you still can get the idea. I'll do it actually even in a different color. Let's do it in the blue. So the graph looks like it has been compressed. You'll also sometimes hear that word used instead of shrink. You'll hear compressed. Does that make sense?
So if you're shrinking the graph is like closer to a shrink,
Say that again.
like if you're shrinking it, it'll almost become
I think you mean horizontal, not straight. So as you're squishing it down, it becomes more horizontal. Yeah. So we're compressing it more towards like the x-axis. Okay, so we're going to take the questions from a slightly different perspective. We're going to actually be given the description of the change that's being made, and we're going to create the equation that does that. And we can probably also sketch a graph of this just for the point of doing so, because we haven't had ones where we've had multiple transformations going on to sketch. But let's talk about what each of these does. This one says right 4, and then it says down 7. So right 4, that's the first piece. Will that happen inside with x or on the outside? It will happen inside. Okay, anything that's affecting right or left is happening inside. Will I add 4 or will I subtract 4? I will subtract 4. So far what I have is grouped inside with x, I am subtracting a 4. And all of that's being squared. That's what it means to be grouped with x, is whatever's happening to x, it's now happening to the 4 at the same time. What about the down 7? Where will that occur? It'll occur on the outside. Will it be addition of 7 or subtraction of 7? It'll be subtraction of 7. And this is my new equation that I've created that will do just this. Now, if you do have a graphing calculator, you can put that in and you can see that it really did what you expected it to do. That's great. If you're trying to graph this and you're given this equation or asked to graph the equation after you created it, you can do that as well. So again, one of the ways to do that is to shift the location, the absolute, or not absolute value, but the graph, typically the basic graph of looks like that, right? And I'm supposed to shift it right 4. So I'll move to the right 4. 1, 2, 3, 4. And I'll move down 7. 1, 2, 3, 4, 5, 6, 7. And then that location, which was originally over here, is now shifted to over here. The graph is still opening up. I don't have any reflections going on or anything, any stretches going on. So this is my first point. And then absolute value graphs and square graphs both have the ability that you go up 1 and right 1. It's just that one of them's straight lines that come out of it, right, the absolute value, and the other one's curved. So I can go up 1 and right 1 on each of these. Up 1, right 1, and up 1, left 1. So here's one of them, and here's the other one. And then I can connect them in a smooth, curved fashion like my parabola. That's not perfect, but hopefully you get the right idea. This one that's solid is the one that's my final result. Absolute value graphs and x squared graphs are very familiar to us, so they're easy to work with when we talk about this, but they don't do a very good job of really showing a lot of the shape being changed because they have the symmetry. The absolute or the square root graph that we're doing on part B has that feature. So as we graph it, you'll see more of what's happening on the shape going on a little bit more on that one. This one talks about several things that are happening. It says it's stretched vertical by a factor of 4. It says it's reflected over the x-axis, and it's going up 3. It's a lot of things. It's 3 this time, right? It's okay. We're just going to go one at a time. Stretched vertically by a factor of 4. That tells you you're going to be multiplying by a 4, okay? It's going to make it narrower. It's going to make it skinny. But where's the 4 going to go? Is it going to go underneath the radical with the x or on the outside of the radical? Outside. And in fact, all the ones that we are doing are going outside when it's stretched or compressed. Ours are only outside. There's another way that you can look at this where you can talk about what's underneath the radical. I think it confuses and muddies up the water more than it helps, so I don't teach it. There's a 4 that's happening outside. That's the first thing I'm doing. I'll erase here in a minute for more, but that's the first piece. Stretched vertically by a factor of 4. How about reflected over the x-axis? Okay, there will be a negative. Reflection tells you there's going to be a negative. It tells you it's reflected over the x-axis. So is that reflection up, down, left, or is it a reflection left, right? It's an up-down reflection, right? It's a vertical reflection, actually. So where will the negative go? Will it go in front, or will it go inside? It absolutely goes in front again as well. So I have a negative over here. So anything that's reflecting it up, down, is reflecting it vertically, just like the stretch vertically, so it goes on the outside. The last one says that it's shifted up 3. So shifting up 3 means I'm going to be adding or subtracting something. Am I doing it inside or am I doing it outside? This one's outside because it says up. Up and down is an outside. Is it addition of 3 or subtraction of 3? Addition of 3. So my equation ends up looking like that. Okay, so that's what the question actually asked us for. I'd like for us to graph it just because we haven't had a chance to graph one with these. So this graph starts out looking, again, I'll do my dotted part of it for you first. It starts out looking like this. That was our basic graph. It says I need to go up 3. So that's actually the easiest thing to fix first is just the location. Should do the shifting part first. So I'm going to go up 3. So here's 1, 2, 3. So I'm going to start at 3 now as I'm making my point. But it's supposed to be reflected. And it's supposed to be reflected down, right? That's where it's supposed to be reflected. It's supposed to be reflected down. So I actually reflect it down from where it currently is. Yes, it's a reflection over the x-axis, but because I did the shift first, the reflection actually occurs from where I did my shift. So the reflection happens to be straight down from where it is. So in other words, instead of going up like this, it's going to go down like that. Okay, so it starts where my point was actually located after my shift. That's where the reflection will start. If it had been reflected left, it would be reflected over here. Okay, so we are going to reflect it down, but we're also multiplying by a factor of 4. So on this one, I went up 1 and right 1. I mean, that's where the point ends up being. So instead of going up, I'm going to go down because I've reflected it down. And instead of going down 1, I'm going to go down 4 because it's a stretch of 4. So I actually end up having the graph down here. And these 2 points, it's not going to look good because it's so skewed. So it won't look super smooth, but it should look like it's doing this really, I don't know, deep feeling or something like that instead of it being so flat. It looks really narrow now. And do you see how I mean that it looks skinnier? Right? It looks narrower than it did before somehow. So it's making it look sort of tall and skinny instead of making it look the way that it did originally. Any questions on that? Yes.
Does it not go to the negative 3 on the y-axis?
Yeah, so that's a really good question. If I were actually doing this in the correct order, I would have started with my flip and everything here first, and then I would have done the shifting of the 3 last. So if you start with the flipping, I kind of like to start with my shifting. That's just kind of me because I think it's easier as a location starting point. But if you're doing things sort of in an order of operations perspective, the first thing we should have done was to flip it down. So if I had done that, I would have been here next. And then from there, I would have stretched it by a factor of 4, so it would have gotten really wide like this, right, moving from the outside in. And then I would have moved it up 3 from there. So that's where it would have ended up if I'd done it in that order of operations. So it just depends on the order you want to do them in. If you shift first, then any of your reflections occur from the location of the shift. Yep.
Whenever you like stretch, like you go forward, I get that you like go down forward. Why did you go over one?
So you always go over. So if you take a look over here at my original graph, let me change my color. My original graph is always, from the original point was there at the origin, and we went right 1 and up 1. So instead of going right 1 and up 1, I would go right 1 and up 4 if I were stretched by a factor of 4. It's always stretching it just the y value. So the x values still shift left or right, whatever you would have normally done. Ours are pretty much 1s. And then we talk about stretching it up taller or down lower. Okay, we're about to shift gears. So any other questions about stretches, compressions, reflections, any of that stuff? Okay, the other topic in our title of our section was symmetry, which we've talked briefly about. Oh, order of transformations. I'm sorry, I was moving things a little bit ahead of myself. I was already on the next part. Order of transformations. So as you take a look at these, this is actually exactly what Noah and I were just chatting about. So apparently it was placed in the notes there on purpose, because probably it fits there very nicely. So as we're taking a look at our order of transformations, if we're working from the inside out, instead of what I was doing, which was shifting things first, then the order of transformations won't ever be able to be confused with the way that we were confusing it as we talked. So as you're working from the inside out, you notice that things that are grouped inside with x first is the negative h. That's the shift that's vertical. I'm sorry, I said it wrong. The shift that's horizontal by a negative h, so it's moving it to the right h if h is positive. And then the next one is the reflections and the stretches. So you're moving sort of outwards next to this piece, right? You're moving to the times a part at the beginning. A is either a positive or a negative number. That tells you whether you've got a reflection. It's either a bigger value than 1 or between 0 and 1, which tells you whether you've got a shrink or a compression. And then your last thing is the shift. So if you want to be careful about how it's flipping and not have to think about, wait, do I flip it from the location or do I flip it from the actual axis? If you're moving from the inside out, it'll keep that in pieces a little bit better. Okay, this is where I thought we were headed, special symmetries. So there are several special symmetries that happen in graphs. The two that we're going to look specifically at because they apply to functions are y-axis symmetry and origin symmetry. So y-axis symmetry is actually what happens, it's called an even function. And you've seen a couple of graphs that do this. The ones we've been working with today, the ones primarily we've been working with today have both done this. So y equals the absolute value of x does this, y equals x squared does this. Right? So they have this beautiful, you look at them and you feel like, oh, look, there's symmetry involved. Right? So we, started by nature, we like symmetry. You look at yourself in the mirror and you kind of want to see that the left-hand side of your face and the right-hand side, they kind of match, right? It's a symmetry thing. That's even. Okay? It's called an even graph when there's that kind of a symmetry. So it splits along the y-axis. The left-hand side of the y-axis to the left of the y-axis and to the right of the y-axis look the same if they have y-axis symmetry. Origin symmetry is called an odd function and does not mean it's weird. Okay? Odd actually means it has origin symmetry specifically. And we actually have a couple of graphs that have done this too, though we haven't talked about them today. We did last time. Our couple of graphs, basic graphs that do this are y equal x cubed and y equal the cube root of x. And we've had some others that don't do any of these kinds of things too, plenty of them. The square root of x that we just did a minute ago doesn't have either of these. So with the origin symmetry, I didn't draw my picture of my evens odds because I've drawn a lot of those today, or my even graphs above. But this one right here is origin symmetry. And what origin symmetry means is it means that if you spun it 180 degrees like a spinner on a game board, it would land on top of itself. Okay? So instead of flipping it left and right like this, and it has the mirror image, right, for your y-axis symmetry, you actually spin it 180 degrees. And if it spins 180 degrees and lands right back down on top of itself, then it has origin symmetry. So this is one of them. The other graph looks like this that we've seen. You can see it also has that same image, right? Some graphs actually have both of these symmetries. If they do have both of these symmetries, then they're not a function. A circle is a very good example. If it's a circle centered at the origin, right, it would have the mirror image on the right and the left. You could spin it 180 degrees and it would match right back down on top of itself. So some graphs do have both. But there's actually a relationship in terms of function. Let me make sure I get this written down right as I'm writing it. The first one is that f of negative x is equal to f of x. The second one's relationship is that f of negative x is equal to, I can't get it written right, negative f of x. So what the first one's actually telling you, in essence, is that it doesn't matter if the x values change from positive to negative, you get the same y values. And if you think about your graphs that you know very well of like absolute value of x, right? The same x value that's positive and negative, so like this point right here and this point right here, if I had drawn them well, should represent the same x value. One's the positive value of it, one's the negative value. They have the exact same y value. So it doesn't matter if I put in 2 or negative 2, I get 2. It doesn't matter if I put in 7 or negative 7, I get 7. So the inputs doesn't matter. The sign does not matter. On your input, I get the same output. This one here tells me that if you put in a negative on the input, it actually changes the sign of the output. And in terms of a graph down here, you can see it happen. So this right here is the value 1, 1. So if I put in a positive 1, I get a positive 1. But if I put in the opposite of it, a negative 1, I end up getting the opposite of it, a negative 1. So I actually get the opposite y value when I put in a negative for x. So I want to show you how this plays out, because this equations that I wrote here at the end, I've sort of argued it from a graphical point of view, maybe a little bit from a point of view, but I want to look at it from an equation point of view next. So we can actually decide based on the equation of a graph whether it's even or odd as well. And here's how we do that. Notice over here, both of these even and odd descriptions have this piece in them, right? They both say f of negative x, okay? That's where we start on deciding if something is even or it's odd, is we start by looking at the equation and we find f of negative x. In other words, I need to replace all my x's with a negative x. Okay, so that's the notation for what that looks like. All of my x's became negative x. Now on this particular function, I've got negative x now to the power of 4. What is the power of 4 going to do to that negative? Cancel it out, right? I've got 4 negatives and multiply 4 negatives together, I still get the same positive value I previously got. It did not change that value at all. Okay, so again, ignoring this negative 2 at the beginning because it's irrelevant at the moment, I have negative x squared. So what happens when I have negative x squared? It's positive as well. So the part that's in parentheses that says negative x squared is a positive x multiplied by my negative 2. So this is negative 2x. And what I want to do is to compare what I got after I did my manipulations with what I originally had. And what do you notice about those two equations? They're different, or they're the same?
They're different. The 2x isn't squared.
Oh, I didn't leave that. That's my fault. I didn't write it. They are different. You're right. They shouldn't be, though. How about now? Are they different or are they the same? Now they're the same. You know, if you put all the pieces in there, it helps. The signs match, right? That's usually the biggest issue, is the signs either are going to stay the same or the signs are going to be different. They're the same. So if I actually had this particular one, they're the same. This is equal to the function itself that I started with. That makes this even. If you were to graph the original equation, that you were given, f of x equals x to the fourth minus 2x squared, it would look symmetric over the y-axis. It wouldn't look exactly like our graph of like x squared, like my y equals x squared, but it would have symmetry just like it did. So this graph is even. B, we're going to do the same thing on every single one of these. We're going to replace x with negative x. Okay. This one's a little bit tricky, and I actually probably need to take a step back up at the beginning and multiply this out to show what's going to happen, because it's really hard to see, because I don't just have a single negative x being squared, I have a negative x minus 1. So if I were to go back up to the original one and I were to multiply out x minus 1 times x minus 1, like this would give me x squared minus 2x plus 1. Is everybody okay with that? So you could either start from that and then put your negative x in there, or you can start from where we are now. I already wrote it down, so I'm going to go with that, and we're going to multiply that one out. So as I multiplied this one out, negative x times negative x would be x squared. The pieces in the middle, the negative 1x times negative x would give, negative 1 times negative x would give me a positive x, both on the inside and the outside, so this is plus 2x. And then my last terms would give me negative 1 times negative 1, which is positive 1. So what I want to compare is what happened when I put the negative x in and what happened when I multiplied it out without it being a negative x in there. So we're going to try this again. Is it the same or is it different? This one's actually different, right? Not every piece is exactly like the piece before. Their x squareds match. Their 1 at the end matches. But they have a different sign on the middle term, correct? Okay. So what that means is that it's not the same, so it's not even. But it also means that not every term is the opposite sign that it was before, so it's not odd either. This is neither. Because it doesn't look exactly like this, which would make it even, and it doesn't look exactly like this, which is what it would take to be odd. So if it looked like this one, it would be odd, the top one that I've now written. If it looked like the second one with the arrow on it, it would be even, and it doesn't look like either one of them. Okay? Even keeps all the signs the same, odd changes all the signs. That's really what matters. If you want to write that down as sort of a note here too, is that this one's telling you all signs stay the same. And in this one, all signs changed. So it was positive, now it's negative, now it's positive. So that's an example of a neither equation. Let's look at the last one. Okay, so this is what happens when I put negative x in for all my x's, right? Okay, so what happens when I cube a negative x? I did a square and I did to the power of 4 before. What happens when I cube it? The negative stays, correct? 3 negatives gives me a negative. It does. So this is actually the same as negative x cubed, like that. What happens when I cube root a negative? Okay, that's a square root. If it were square root of a negative, it would be an imaginary number. A cube root of a number that's negative, it comes out. So imagine, I'll do one that you're familiar with. If you had the cube root of negative 8, I better put it negative, that's what I just said. Negative 8, this would be negative 2, because negative 2 times negative 2 times negative 2 gives me negative 8. I can have an odd number of them to still give me a negative underneath. So you're right, the negative actually will come out of the cube root, just like the negative over here comes out in front of the 2 as I'm working with that. So comparing this to where I started, what do you notice about the signs? Somebody said what? They're all opposite. Every single one changed, right? So in our first example where it was even, all the signs stayed the same. My second example where it was neither, some of the signs stayed, some of them changed. My third example here, they all changed. And when they all change, the graph is odd. And again, if you were to look at this graph, it's not going to look like the x cubed graph exactly, but it's going to look like if I did the spinner thing, right? Spin it around 180 degrees, it lands right back down on top of itself. And we have a graph that's odd. While you are certainly welcome to check your grapher or to check a computer or your phone or whatever to graph these and to ensure that you think that you did get them right, even odd or neither, the equation part is what I'm looking for. Okay, it's the manipulation of the algebra that we're focusing on for now. Okay, we'll talk more about some graph stuffs later. So as you're looking at these, make sure you're showing the f of negative x just like we did on this and the comparison back to the original function. Okay, we're done. Section 2.3 will be due on Thursday. Quiz as well, 2.1, 2.2, 2.3 on Thursday. Have a great week, guys.